Bismillahirrahmanirrahim. So today we are going to be covering chapter 17. So a long time ago, when I was writing this book in the 90s, there were articles written by Efron and Morris which were aimed to popularize these techniques. And basically at that time the discussion was in terms of Stein estimators. This was actually a red herring, and that was not the thing to focus on. But at that time, actually, the Stein Paradox was a very surprising thing, because what the Stein Paradox said is that if you are estimating three normal means, then the classical estimator, which is very strongly supported by a huge amount of theory, x1 is normal with mean theta 1, x2 is normal with mean theta 2, x3 is normal with mean theta 3, then x1 is the best estimator for theta 1, x2 is the best for theta 2, and x3 is best for theta 3. Now what Stein said was that in this situation, if you have a quadratic loss function, then you can dominate the best estimator. So the Stein estimator is better than the natural estimator. And it does something very strange. It says that, okay, in estimating theta 1, you make use of x2 and x3, which is very strange because these three components are independent. So x2 has no information about theta 1 and x3 has no information about theta 1. So how can you improve an estimator of theta 1 by using irrelevant information? So this was what the paradox was. And basically the whole discussion was about this paradox and how, first of all, there was the feeling that this is a mathematical trick and it does not have any relevance to applications. So what Efron and Morris did was that they translated the Stein estimator into an empirical Bayes format, and they showed that they were very, very close. And then the empirical Bayes estimator has a very natural justification, so they said that this is why the Stein estimator works. So then they also said that the resistance to use of this estimation is because the improved estimation is likely to be unimportant, minor gains. So they actually came up with situations like the baseball example where there are significant gains over conventional estimators. And then of course the Stein estimator was designed for a very specific, very special situation. And in general you have many variations, so Stein estimator had very difficult mathematics, so to carry it over to other types of situations was not so easy. That is where the problem with the 45 came in, that Stein estimator requires equal variances, so you have to have the equal number of battings in order to get equal variances. And then of course there was lack of experience. Nobody has actually used these estimators, so you have nothing to build upon when you start doing this. This is the first time. So now the thing is that even at the time I wrote the book, it was not entirely clear, but it had become quite clear at that time, and since then it has become much clearer that Stein paradox is irrelevant. It is a mathematical trick. It doesn't matter. Why it works, that also has been understood, because basically it works not because the three problems are related. They are related through the loss function. So basically, and the interesting thing, there is a mathematical depth to this. It cannot be done with less than 3 dimensions. You have to have 3 or more parameters. So it has to do with the fact that in 3 dimensions you have lots of room to maneuver, which you don't have in 2 and certainly don't have in 1. So it turns out that there are ways that you can arrange things so that by mixing up all the 3 problems, that when your estimator for theta 1 is bad, it is compensated for by better estimation in theta 2 and theta 3. And so it's not that you can improve theta 1's estimator by using information from x2 and x3, which is impossible.
All these thetas are found, should be found?
They are all completely different. Thetas are the unknown parameters. Like wheat yield in Pakistan is theta 1, and you have estimates of crops. Theta 2 is the rainfall in Brazil, and then again you have data on rainfall. And then theta 3 is sunspots, which are observed every month, and you have data on sunspots. So how can you use wheat yield and rainfall data to estimate sunspots? You can't. But the point is that if you use the Stein estimator, then when the sunspot estimator is made worse by the information, then the other 2 components will improve, and things can be balanced in such a way that the overall squared error loss is better for the Stein estimator. But this is just a mathematical trick. It doesn't have any real relevance to real world problems, because what happens is that the amount of gain is rather small. There is some substantial gain in a very small portion of 3-dimensional space. So now the thing is that if you have 3 separate problems like rainfall and sunspots and wheat yields, then generally you will not have a quadratic loss. You will not have a loss in which people will say that, okay, if my estimator for wheat yield becomes worse, I don't mind as long as I get better estimates of sunspots. And generally speaking, people will be interested in their own components. And this is the key issue, which also arises in the last part of this chapter, that if we are estimating census undercounts in different states, then the overall loss is improved, but for any particular state you cannot say whether it is better or worse. So if I am concerned with my state, then I will not be concerned, I will not be happy to have an estimator which makes my estimator worse, but it gets gains in other states. I want to guarantee that my estimator is better, and that is not done by the Stein estimator. So the thing is that, so that's the point, that it is a mathematical trick. The second thing is that the gains are extremely high, but only in a very small neighborhood, which means that if you have no prior information about the 3-dimensional space, then there is it's hopeless, because the chances of hitting a 3-dimensional is a very large place, and the chances of hitting making a random guess and hitting the true parameters, which is what you need to do, is virtually 0. So there is no real chance of making significant gain unless you have genuine prior information. So if you do have genuine prior information, then you should use empirical Bayes, because that's the situation where prior information. Stein estimator works without prior information, but that is a trick, because although it is true that mathematically the Stein estimator is superior, the fact is that if you don't have prior information, you shouldn't be trying to use it, because the gains will be non-existent, because you can't hit a point in 3-dimensional space just by chance. You have to have some knowledge. So if you do have prior information, then you can get significant gains, but then Stein estimation is not the right tool, because Stein estimator enforces minimaxity. Minimaxity means that it is better than the a natural estimator, which is the classical estimator. Now, the cost that you pay for this municipality is very high. So you have genuine information. Stein Estimator allows you to buy insurance that if the information is true, then you will gain less. But the information is false, then you won't suffer any loss. So that's what the title of this chapter reflects. It is called Utilizing Information of Uncertain Validity. So basically, if you have some prior information, you don't know whether it's true or not, Stein Estimator allows you to use this information without any risk. But this is at a cost. The cost is that if the information is false, you don't suffer any loss, but the information is true, you don't get any gain. So ultimately it's useless in that case as well. So there are ways. There are ways to do things. So basically, then the attention shifts to empirical Bayes estimation. Now, in empirical Bayes estimation, you have prior information. You use it. You get significant gains. But if it is wrong, then you have significant losses. So then there is something which actually Efron came up with, which is called limited translation estimator. And so the limited translation Bayesian estimators have the property that although you suffer loss when your prior information is wrong, the loss is limited, it is bounded. Unlike the standard empirical Bayes, just like the Bayesian estimator, it gambles everything on its prior information because it assumes that the prior information is valid. So when in that situation, the Bayesian estimator does brilliantly, but if the prior information is wrong, then it does hopelessly bad. So the empirical Bayes is similar to Bayes in that respect, that it also gets you good results if the prior information is correct, and it gives you very bad results if the prior information is very bad. So now the limited translation estimators of Efron are compromised. They give you very good results if the information is good, but they limit the loss if the information is bad. So you have still loss, you're not as good as the classical estimator.
So what are the type of limitations?
Limitations का क्या है?
Limited translation estimator,
it just makes sure that the Bayesian estimator doesn't deviate too far from the classical estimator.
based on certain conditions.
No, it just looks at the distance between the Bayesian estimator and the classical and it says the maximum distance should be this much. So that's it. It's very simple. So basically, once you use the empirical Bayes estimator, then all of these four objections that we have become completely different. Now, the first thing is that this is no longer a mathematical trick because the empirical Bayes is solidly motivated. It is representing genuine use of a prior information. The gains are very high if the prior information is very large, and that can be seen in very practical examples. And there is no difficulty in adapting the empirical Bayes method to any sort of situation. We have seen that, and in fact that was one of the things that I was trying to show you, that in the four examples, every single mathematical detail is different, the data density is different, the prior is different, but the methodology is exactly the same. So this is the thing that I have been trying to teach you, that at the meta level, and once there is the detailed mathematical analysis, that's entirely different from each example, but overall from the higher level perspective, it is the same. You're doing exactly the same calculations, and if you interpret things properly as precisions and data means and prior means, then you see that the formulas are also the same. It's just the technical details are different, but the interpretation of the formulas is about the same. So basically that's the so the thing to do is to use empirical Bayes estimators. Now the very interesting thing is that empirical Bayes was not has not been used much in econometrics. This is what I wrote in 90s, and I haven't actually checked, in fact, what has been happening recently. But basically, there was a early adoption problem that as soon as empirical Bayes estimators were introduced, very early, not empirical Bayes, Stein estimators, very early econometricians tried to use them and found that they don't work. So basically the thing is that that was bound to happen because what they were doing was using the wrong type. There was not enough learning about these. So now it is possible to use them, but the impression has been created that empirical Bayes doesn't work in econometrics, or rather Stein estimator doesn't work in econometrics. So it is used very little. Also, there are some other complications which existed about Stein estimator in the past, which were not taken into account, or which were not available. Now the solutions have been found. I'm going to go over a few examples of how empirical Bayes methodology is used in regression models, and I'm going to discuss real world examples. I'm going to do this now. So basically, if you have a regression model, it has the form y equals x beta plus epsilon, where epsilon is normal with mean 0 and variance sigma squared identity. Now the empirical Bayes methodology requires some prior information about beta. Now there are two ways to write down prior information. One is in the form of linear restrictions. So this is a general type of a linear restriction. This can equivalently be written as these are two different equivalent ways of writing a prior restriction. Basically, one says, for example, that all of the betas are the same. This is one linear restriction. This is actually n minus 1. If there are n k parameters, then there are k minus 1 restrictions. There is only 1 degree of freedom. And you can write this in this form by writing the R matrix as 1 minus 1 zeros. That will and put R equal to 0, so that will say beta 1 minus beta 2 equals 0, and then put 1 minus 1 on the diagonal again, 1 on the diagonal and minus 1 on the next entry. That will say beta 2 minus beta 3 equals 0, and so that way the R matrix will have k minus 1 rows and k columns, and that will the restriction R beta equals R says beta 1 equals beta 2 equals beta 3, and so on up to beta n minus k minus 1 equals beta k. So that's one way. The other way to write it is that beta is equal to, this can be the identity matrix, is just alpha. So there's one alpha which is just the same, and then beta 1 equals alpha, beta 2 equals alpha, beta 3 equals alpha. So these are two equivalent ways. If you know linear algebra, then you can understand what is happening. Basically, when you put m restrictions on beta, then there is a total of k parameters inside beta. When you put m restrictions, that means that m degrees of freedom are taken away, and k minus m is free. So you can either say, okay, these are the k minus m free parameters, and then everything is obtained from these by linear restrictions, or alternatively, you can say that some m linear combinations of beta are 0. So these two are equivalent, and for mathematical purposes, both of them are useful. And you can write, if you're given restriction in one form, you can convert it to the other, and vice versa. So both of these forms are useful in calculating the Bayesian estimators. Now the issue that we want to assess is that if this information is known and certain, then this is a situation which is well known to econometricians. You impose the restriction and you maximize subject to the restriction. So there is a constrained estimator which you can easily get from this form, and because you just substitute in, you get y equals xh alpha plus x alpha naught plus epsilon, and so y minus x alpha naught is equal to x h alpha plus epsilon. And now you use the Ols estimator for alpha, which is xh transpose xh inverse times xh transpose y, and so you get the estimator, the Ols estimator for alpha hat. The other estimator which you can get from here also, which is exactly the same, is something like r x transpose x r transpose inverse. It has some complicated formula like this, which is actually written in the book in an earlier chapter. So anyway, there is a constrained estimator. This we can call beta hat here is x transpose x inverse x transpose y, and beta plus is the constrained estimator, which is I will give it in the other form. So this is the constrained estimator. So if you know for sure that your restrictions are valid, then you maximize likelihood subject to the constraint, and using the Lagrangian method you get this estimator, or alternatively use the substitution, and this is the optimal estimator. So now we are considering the situation where this information is of uncertain validity. You're not sure whether or not this is true. You think it might be true, but you are also concerned that maybe this information is not correct. The example being that we think that the players all have the same ability or very similar ability, or maybe they don't, but it seems likely that they do. They're all international competitors, so we have this information. We would like to impose it, but we are not exactly sure. So the Ols methodology, the econometric methodology, offers two options. You can either go with imposing the information, which means you use the constrained estimator, or you ignore the information, which means that you use the Ols. So one way is to decide that, well, think about the information. If you trust it, then impose it. If you don't trust it, then use beta hat. So then there is a more sophisticated methodology which was developed for this situation precisely, which says, okay, do a hypothesis test. Set this up as your null hypothesis. Then there is an F test which can be calculated, that tells you whether or not the data accepts this. So you do an exception and rejection, and if you accept this null hypothesis, then use the constraint estimator, and if you don't accept the null hypothesis, you reject it, then use OLS. So this is called the pretest estimator. Now actually what the Bayesian methodology does is it combines these two. This is what the methodology. It combines these two estimators, and it basically assesses, it says, okay, this is uncertain information, so to add an epsilon here, or add a error here, and then estimate the variance of this error. Huh? So if this error is very large, that means that this constraint is useless. If the error is very small, then this constraint is useful. So then it basically does a smooth combination of these two estimators depending on the variance of the error. So this is a very intelligent way to use the prior information. It assesses how reliable the prior information is. In fact, you can show that the assessment that you do is quite close to the F statistic that you get for testing this information. So basically you can say that you test it, but instead of doing accept reject, the test gives you an idea of how valid this information is, and use that as a weight to mix the two estimators. So basically you shrink the beta hat towards the beta plus, and the shrinkage is based on how good the prior information is. So this is a very sensible and intelligent method, and you can prove mathematically that this is optimal in the sense that it is better than the pretest estimator. Pretest estimator is a risky method because you can easily make type 1 and type 2 errors in testing the hypothesis. So it's a discontinuous use of information. If you with slight change you switch from one thing to another, and that's not usually a good way to use information. You can prove that discontinuous use of information will lead to a an estimator which can be dominated by the empirical base. So empirical base is a better way to use this information. So that's the general methodology. The equation 17.2 is telling you how to mix the prior, the restricted estimator and the OLS estimator. So basically that's a very crucial formula, because we have learned this formula in the scalar case. Now in the matrix case, it's quite interesting. What happens is that you again get a precision weighted average, but the precision exactly as you do in the scalar case, but the precision now is a matrix, it's not a scalar. So you get precision matrix, which is the inverse of the covariance matrix, and you use the precision matrix, multiply the data-based estimator, the ML, and then you use the prior precision and multiply by the prior mean vector, and then you divide by the sum of the precisions. Now division doesn't have any meaning for matrices, so what you do is you take the sum of the precision matrix and you take the inverse of that, and that's like dividing, and you pre-multiply by that. So it's a very natural generalization of the empirical base. So now basically all of this chapter, all of this part is providing the theoretical background. I'm going to skip over that.
How do you fix the value of V? You have insert here.
Question 17.2. V squared.
V squared is that's the prior variance. So we estimate that in empirical base.
Linear restriction के केस में जहाँ पर hypothesis testing करनी है.
हाँ, so we introduce an error into that relationship. The error has a variance. We estimate that variance using empirical base, and then we.
मैं कह रहा हूँ वो error की value जो हम fix कर वो कैसे fix करेंगे कि ये error हम ये यहाँ पर introduce करवाना है.
we don't fix a value of the thing. We assume that the prior information has some error in it, and then we estimate the variance of that error using the standard empirical Bayes methodology. Alright, so this is the Fay and Harriet article. There is a background. There were yani census was carried out now in the USA, and in 1970, every 10 years they have a census. In 1972, there was some law which was passed that every local government will receive some amount of money based on the average per capita income in that place. So now there were 39,000 small units, let's call them like the Union Council. So the Union Council is a small unit. The census, at the time that the census was being done, the people who were carrying out the census did not know that they would be asked to produce average income estimates for these 39,000 places. So they didn't design the sample to capture that. They had a random sample from the whole county, which was a large grouping of these union councils. That was fairly accurately estimated by them because they knew that they would want that. But within the county, each union council they had random sampled, and some of the union councils had large number of people picked from, and some of them had small. So it was not clear. Yani when they were asked to produce estimates for these small places, the union council, their sample was not designed to answer this question. So initially they thought about the problem. They came up with a very simple solution. They said, okay, if we look at a union, if we have in our sample 500 people or more sample from that, then we can say, okay, that we have a reliable estimator, and so we use the average income for those 500 people. And if we have less than 500, then we just go with the county estimate. So this is a very simple situation, and this should be, it should be clear that that is exactly the same type of situation we have been thinking about for a long time in empirical Bayes, that we have two different possibilities. We can go with the individual fire alarm, or we can go with the bigger unit. And these two are both reasonable estimators, but the question is that how do we combine these two? So there is this, either we go with one or the other strategy, which is the same as this idea of the restricted versus the whole, or can we find a way to mix these two estimators? And that's basically what the empirical Bayes estimator does. Now there is one more complication which arises here, which makes this problem more of a regression problem. Previously we just had counts. Basically the thing is that, okay, so here we have y is the m/1 estimator of census estimates for each county. Now this is a mistake in the text. It is not for each county. This is for the small places, the union councils that we are talking about. The 39,000 counties are much fewer. So now, these are the small places within the counties that we are trying to estimate. Now we assume that, okay, the estimate that we have, which is yi, which is there is a sample. Every county has some people, and every union council has some people which have sampled, maybe 5, 10, 100, 500, 1,000. It depends on various things. So we assume that this sample is an estimator of the true county union council mean, which is theta, and then there is some error. Error is the sampling error. Now the error that we have is not going to be homogeneous. It's not going to be, in the standard regression model, the errors are assumed to be IID, they are all assumed to have the same variance. But here this is not reasonable, because actually in each county we have different sample sizes. So the sample size governs the accuracy, and basically what we get is that the variance estimator, which the Census Bureau has an estimator of, is V hat I is equal to 9 times y squared divided by n. Y squared is the estimate based on the sample, because basically they have a coefficient of variation which is the proportion of the estimate divided by its standard deviation. This coefficient of variation is 3 over square root of n, where n is the size of the sample. This was estimated by the Census Bureau. So now on the basis of this we can calculate, from the coefficient of variation we can calculate the variance of the normal distribution. So we get the epsilon is normal with mean 0 and variance Vi. For the purpose of for theoretical purposes, all that matters is that each epsilon has a different variance, and we know what that variance is. Actually, we don't even know what that variance is, because we are estimating it by V hat I. We're using the county estimate. But this is just like the binomial, where we take the variance. It has theta times 1 minus theta. Theta is unknown, but for the variance we pretend that it is known. So now this is one part. So basically one part of the problem is that the errors are heteroscedastic. This problem causes no difficulty for empirical Bayes. That is, it causes a great difficulty for Stein estimation, because Stein estimation doesn't work unless you have equal variances. But it causes no difficulty for empirical Bayes. It works just as well, and without any change even in the calculation formulas. Everything works just without any difficulty. But now the complication is that we also have some additional information about each small place the Union Council says. I'm calling them. The additional information is that we have tax returns which are available from the revenue. So tax returns provide a lot of accurate information about incomes. We also have property value data which is gathered. So that also provides some information. And we also have the county PCI, which is the bigger unit. So we can think of a model for the theta I. Theta I is the average per capita income within the Union Council, and we can make a regression model. This is a function of the tax returns which is observed, the property values, and the county per capita income, which is the bigger unit. Now the original Census Bureau procedure which they thought of was to say that, okay, we ignore the property values and tax returns, and we look at the county PCI, and basically if the sample size is bigger than 500, then we substitute county PCI for then we use just YI, which is the place income, or if it's less than 500, then we use the county per capita income. So that's obviously a very crude and very unpleasant type of estimator, because we are throwing away a lot of information. So instead, what we argue is that we create this model. So we have initial model y equals theta plus epsilon, and epsilon is normal with mean 0 and variance V, where V is a diagonal matrix with VI's on the diagonal. Then we have a model for theta. The capita income is x beta plus u. So the per capita income in the Union Council is a function of, this is this is a t by 4, 4 by 1. There are 4 regressors. One is a constant term. The second is the tax returns. The calculation of income that you get from the tax returns, and then you have the property values, and then you have the county per capita income. These are the four regressors that we have. So they will determine to some extent theta, but how accurately do these determine, that we don't know, and that we capture in this error term. So these four variables will give us a lot of information, but how much information do they give us? That is something we don't know. That's what makes this information of uncertain validity. So now one possibility is to estimate this regression model by just plugging in here, calculate beta hat, and then we will just get, then we just set theta equal to x beta hat. That is the imposing the information. That is saying that, okay, this information is certain, there is no error. So if there is no error, we can just substitute x beta, we can calculate, we can estimate beta, and x beta hat will be our estimate of y. That is the constrained estimator that imposes the information. That is equivalent to assuming that the variance here is 0. The other estimate is to just throw it away and just estimate yi equal to theta I. So now actually you can see that the Census Bureau original estimator is a special case of this procedure that I'm taking, where x beta is not taken to be x beta, it is just taken, there's just one regressor, that is the county per capita income, and then we say impose this if the sample size is bigger than 500, and ignore this if the sample size is less than 500. So that's not a very appealing estimator. So now we go to the empirical Bayes methodology, which says that let's try to find out how much error there is. So what we do is we get to the basically we are trying to find the marginal distribution of y. So basically y depends on parameter, parameter depends on hyperparameter. We want to get rid of the parameter and relate the data to the hyperparameter in order to estimate the hyperparameter. So that's easy, we just substitute. So we get y equals x beta plus u plus epsilon. So this is the new error, and the new error will have covariance matrix which is equal to v plus some I think I've called it A times identity. So both of these are diagonal matrices. So basically we are getting the variances are Vi plus A in each coordinate. This is a structure which is familiar. Now we can estimate beta. And this estimator is the empirical Bayes estimator of beta. And then we can estimate the VIs are supposed to be known. The A is what we need to estimate. So this is done in a two-stage process. So we have y equals x beta plus nu, where nu is the combination of these two errors, and nu has a diagonal covariance matrix. And on the diagonal we have omega I is equal to Vi plus A. So now the well-known GLS estimator is beta tilde equals x transpose omega inverse x transpose omega inverse y. So this is the methodology. I start with an estimator of A. Initial guess, A0. It can be anything. You can start with 0, for example. Then you have your omega matrix, so you estimate your GLS estimator. Now once you have a GLS estimator, then you can construct an estimator for A. And in the text, I have given two methods. One is based on maximum likelihood, other is based on method of moments. It turns out that this doesn't matter very much. I mean, as long as you have a reasonable estimator, you get similar results and you get similar efficiencies of estimation. So basically the validity and the utility of empirical Bayes depends on the structure of the additional information that you have provided, not on exactly how you estimate the parameters. So I will give you the simple method. So what we have is that you can break this up into rows. This is a t by 1. This is t equations separately. You have y1 equals x1 beta tilde plus nu 1, and then y2, etc., etc. All of these are. So now pretend that beta is correct and known. First we have pretended that A is known. Now we are going to cycle back and forth. So then the expected value of yt minus xt. X is the tth row of the X matrix. Assuming that beta is known, so then the expectation can be calculated. This is just vi plus A. Because this is a diagonal matrix, so there's no, and I'm assuming that beta tilde is known and is the true value. So now we look at yt minus xt beta tilde squared minus vi, and this is an estimator of the A, which is the prior variance. So I can just average this. And one thing that I have done is to take the plus part, the positive part, as usual. Because this is an estimator of prior variance, it can't be negative. So if it comes out negative, we just truncate it 0. So this will be our A hat, first estimator of, or we can call it A hat 1. If A hat 0 was the initial guess. Now I have A hat 1. I can estimate my omega matrix again, and now I have omega, so I can get the GLS estimator for beta, and then I can iterate back and forth, and this procedure is guaranteed to converge. There is a mathematical theorem about this which shows that this is going to converge. So eventually you will get A's and beta tildes, where the beta is the GLS estimator and A satisfies these equations simultaneously. Both of these hold. So that gives you your estimator of A. A is a measure of how accurate your prior information is. If A is small relative to the VI, that means that your prior information is very accurate, and that means that your estimators of the place incomes will be strongly shrinking towards the common mean. So it will be like imposing the restrictions. And if A is very large, that the prior information is very inaccurate, and then you will be basically using your original place income. So this is called the Fay-Harriott methodology. I mean, these are the authors who invented this methodology. Now they did a couple of refinements. One of the important ones was that you get estimators at the end of theta hat 1, theta hat 2 for all of the union councils. Now a collection of these union councils is all within a particular county, so you have a very accurate estimator for the county. Now these estimators are not guaranteed to match, but when you aggregate all of the places, then you get an alternative estimator of the average county income. So they said, okay, let's adjust this to match. So we multiply this by alpha by some proportion, where alpha is chosen to make sure that the sum of the per capita incomes within a particular county matches the overall. So that's one important adjustment that you can make in this situation. And basically there are some other, but this is the most important one. So basically that's called the Variance Estimator. Now they actually tested this because the Census Bureau keeps doing samples, so they did some. The census itself is a full and complete sample of 100% of the population, but they keep making small size samples. So they had various other samples and they cross-checked to see how this methodology works compared to the original 500 or more, and they found that this was much more accurate on the places where they could test. So, one of the important things about this is that in the cases where the particular union council has a large sample, this doesn't make any difference. This is very important to understand, because the shrinkage is zero, because you see you're looking at A and you're comparing it to VI. So if VI is very small, that is the data variance is very small, then the prior will disappear. But for counties, for union councils where the sample size was very large, then the VI will be very large, and then there is a lot of shrinkage. So basically all of the gain occurs in those places where the sample is small. So, and there is not much gain in the large samples. And the other thing is also true that this is not an estimator which is dominant. This is very important. That is, it is not true that for every single place you get a better estimator. What happens is that the overall average estimator is better, but for some places you can have that it can happen by chance that the small random sample gives a more accurate estimator than the empirical Bayes adjustment. So overall the error is much better, but individually for any single place you cannot guarantee. It is the sum of the errors which is improved, not individual error, place by place. Okay, so that's the end of this particular example. Now we can go on to the next example. So when are you giving me your homework? Okay, so we did this validation. Now we get to the very interesting example of Friedman and Navidi. That's a bit complicated. Let's see if there's another one here. Okay, yes, this is Carrington Zaman. Okay, so I'm going to skip the Friedman-Navidi, which has some additional complications that we haven't discussed before. I'll try to cover that next time. I'm going to go to the Carrington-Zaman model, which is almost the same theoretically. So okay, so So the problem of interest is that we have yi, which is the data is on is a sample from labor sample survey, in which we look at a person who is working in different kind of industry, food industry, auto industry, and so on. Person loses the job, then he finds a new job. So now what is the difference between the wage in the new job from the previous one? So this is if the worker has been displaced, then normally it is expected that there is a negative shock. The new job will not be able to provide him with the same wage that he had previously. Now the question is that each industry has different characteristics, and there are 50 of them. So we look at the average wage change in the industry, and we want to estimate for each industry the amount of the unemployment shock is the name. What is the shock to income that arises from unemployment? So we have some regressors which are related to the characteristics of the industry. Those are like the amount of human capital required. I haven't mentioned these here. They are discussed in the paper. Paper has been uploaded on the website. So basically it can be things like, how much training does the industry, if it's an unskilled labor using industry, then we would expect that these are the things that will cause a difference. So we have some regressors. So in each industry we have values of betas, and we think that probably the different regressors have different coefficients in different industries. But the sample size is fairly small, because even though the original labor force survey is quite large, but we are looking for very special kinds of people, the people who lost jobs and then they got new jobs within some 3 months or 6 months, I don't remember. So this makes the sample size very small. In some industries there is very little turnover, so the sample size is very small. In the other industries there is lots of turnover, so we have a large sample size. So now again we have the same problem, that if we assume all the betas are the same across the industries, then we can just aggregate all the data and we get one estimator for all the industries. But this would actually lose the job, because one of the main goals was to find out how the industries are different. But at the same time, if we estimate each industry separately, then what happens is that the larger industries are accurately estimated, but the smaller industries are very inaccurately estimated. So we might not get any very good results from that. So again, this is a situation which is adapted to the empirical based methodology, that we have some information of uncertain validity, and so we want to impose this, but not impose this with the confidence that we don't want to substitute restriction, let's see what happens next.
So this aggregate change can be within the industry or across a different type of industries?
Actually, I don't remember. I think it's allowed to. Yeah, I mean the wage changes, and the person can shift out of the industry also.
Because the variations can be observed within the industry as well.
Absolutely, that is true. But I don't remember exactly. I was actually David Carrington was on the labor economist, so I let him worry about those details. I told him how to do the estimation, which he didn't know. Okay, yeah. So this is the setup. Just like when you have samples from normal distributions, different ones, then you reduce the sample to two sufficient statistics, which is x bar and s squared, and then you consider the. So here, first we think of each industry separately. So we get beta hat I, which is normal, with mean beta I, and variance sigma squared I, xi transpose xi inverse. So we have each industry is estimated separately by OLS, and the OLS estimator has this distribution under standard conditions. And again, just like we've always been doing, there is a sigma hat squared which you get from the OLS estimators, a standard error of the regression, and I'm going to pretend that sigma hat I squared is equal to sigma squared I, just to simplify the calculations. The hierarchical Bayes methodology, and even in empirical Bayes, it's possible to adjust for this variance, but it just makes things more complicated. And at this point, I'm trying to convey the idea first. The technical details will be later. So now there is some idea that all of the betas are the same. So I'm going to call this matrix the inverse of this matrix, which is 1 over sigma squared I xi transpose xi. This I will call PI, the precision matrix of the ith estimator. So now it turns out that this is a formula which can be derived, that suppose we just aggregate all of the data. So we just throw all the industry, we just lose this I, which is the industry marker, and we say, okay, all of the industries have the same coefficient beta. Then we just do the aggregate estimator. So the aggregate overall estimator beta hat, which is the restricted estimator, turns out that it is just the precision weighted average of the separate OLS estimators. So, so this is the restricted estimator that we want to shrink towards, and the unrestricted estimator is beta hat I. So now, basically then we put the prior information that beta I is normal with mean beta and some prior covariance matrix sigma. And now this beta is estimated by this beta hat. That is the best estimator of beta under the assumption that the restriction is valid, that all of the betas are the same. So now the next problem is to estimate this sigma. That is the key to the empirical Bayes estimator. So now to estimate this sigma, it turns out that there are different methods. One is called the G prior, and the G prior that was introduced basically one method which is the most a natural one is to say, okay, let sigma be unconstrained, don't put any assumptions. So we have sigma ij, the covariance matrix here, and we can try to estimate all of the n by n parameters in sigma. That would be the natural thing to do. It turns out that this doesn't work very well because there are too many parameters to estimate, and so when you get this kind of we are estimating a weak relationship. Y relates to beta, beta relates to the covariance, and now with weak information you get imprecise estimators. When you get imprecise estimators, then this causes difficulties for the empirical Bayes estimator. So one needs to impose some structure on sigma in order to get reasonable empirical Bayes estimators. So what structure? There are two structures which are useful. There are many others, but these two are the most common. One is to say that sigma is equal to lambda I xi transpose. Yeah, that's right. So this is called the G prior. Once you put sigma as that, then it combines with the data density, so the calculations become quite easy. So basically, when you are trying to estimate, you get beta hat I is normal with mean beta and covariance sigma squared I plus lambda I times xi transpose x inverse. These two covariances add just like so because the matrix part adds conveniently, so you just get sigma squared I plus lambda I. Then it's possible to calculate an estimator of lambda I quite easily, and then you can use that. I use this, and the other option which also works quite nicely is called the D prior, and that is to assume that sigma is a diagonal matrix. So we only have sigma ii, the diagonal elements which are non-zero. So it turned out that in our application we tried both of those, and the D prior worked better. So I am showing the calculations for the D prior.
So this lambda is a G prior only?
Yes, the lambda, well, the G prior, the main thing is that the sigma is proportional to the data covariance matrix. So it combines with it nicely. So now in the D prior, we have beta hat I is normal with mean beta. Now you're looking at the marginal distribution. I'm going to get rid of the parameter. So beta I is normal with mean beta and some covariance. So basically it becomes sigma squared I xi transpose xi inverse plus omega, where omega is the prior covariance. And now this is a diagonal matrix by assumption. So to get our empirical Bayes estimators, I need the estimators of these omegas, and so that is done by looking at the components one by one. So beta hat I1 This is the estimator of the constant term. Beta hat I2 is the estimator of the coefficient of the first variable, regressor, and so on. So just look at any one of them, it doesn't matter, they're all estimated in the same way. Okay, now here we have the overall beta hat, which has been estimated already. So this is the estimator of the constant term from the aggregated regression. Now the expected value of the square of this is equal to the variance so it's sigma squared I di. Di is the diagonal entry of xi transpose xi inverse. The entry on the diagonal, that's the variance, plus omega I. Right. This I is different from that I. So the ith-tree. Yes, this is going to be 1. This is the ith industry, the first coordinate, the first parameter. So now the first parameter has prior omega 1, which is the same across industries. So now I can do the standard thing, which is to look at beta hat I1 minus beta hat 1 squared minus sigma hat I squared di. Di is not di, it's d1. This is the first entry, di1. This is the first diagonal entry in the xi transpose xi inverse matrix. So this is our estimator of omega 1, but I want to take the positive part of this, and then I can sum it over all the industries, 50 industries, and take the average. So this gives me an estimator of omega 1, and similarly I can estimate omega 2 and omega 3, and so on. There is some fancy work done in the paper in which basically you see the difference between beta hat I and beta hat, because when we estimate this, so you lose some degrees of freedom. In fact, given the number of degrees of freedom lost is equal to the number of regressors, so you can make an adjustment by, instead of dividing by 1 over 50, you can divide over 150 minus 4, which would take care of this problem. And that's done in the paper, but it turns out it's not so important. So this is how you estimate the omega. Once you have an estimator of the omega, then the next step is quite easy. Now we have a situation where this is our ith industry. Now we look at the industry alone, not in conjunction with all of the others. And now we have beta hat I is normal with mean beta and covariance omega. This is the prior distribution. Now I have a beta tilde, which is the, beta hat is what I've been calling it, the aggregated estimator for the beta. And now I have a omega hat, which is my empirical base estimator. So now this situation is very standard, and in this situation, you can get the estimator. This is the Ols estimator. The Bayesian estimator of ith estimator based on this prior is equal to the precision here, omega hat inverse is the prior precision plus the data precision, which is actually 1 over sigma squared I xi transpose xi inverse times, this is matrix multiplication now, omega hat I inverse times the prior mean, which is beta hat, plus 1 over sigma hat I squared xi transpose xi times beta hat I, which is the data means. Now here there is some cancellation. Beta hat I is x transpose x inverse x transpose y. So this xi transpose cancels, so you get 1 over sigma hat I squared times xi transpose yi. So this is the the empirical Bayes estimator. This is the Bayes estimator if omega was not estimated, and it becomes the empirical Bayes estimator if omega both we are estimating beta hat and omega. So the classical Bayes estimator specifies what beta is and what omega is, and that's a useless estimator because you never know how to specify a good prior. But the empirical Bayes estimator is a useful alternative which creates a reasonable estimator of this situation. And that's it. This is the estimator which we used, and it turned out that basically again we got the same results, that in industries which had very large samples, there was no difference that was made by this estimator, because basically the this sigma hat I squared was small, so the weight being received by the OLS was large, and in that case the empirical Bayes estimator was nearly the same as the OLS estimator. In the cases of the industries where the sample size was small, there was a lot of difference, there was a lot of shrinkage, and in general the estimators of the empirical Bayes were much more sensible in the sense that they had the sign that you would expect from the theory and the magnitude that you would expect from the theory. And there were some other ways that we could show that the variance of these estimators was low. They were very clustered, which is what we expect. In the paper we argue that these are better estimators, but we are fairly cautious in making these claims because basically it's a self-justifying procedure in the sense that once you impose the prior, the estimators that you get are consistent with the prior, they are closer together, they have lower variance. All of this is guaranteed by the method, so to say that this is a virtue is not quite correct in the sense that all of this is true provided the prior is correct. If the prior is correct, then automatically these estimators are better. So basically what we are arguing is that the prior is correct. And it can be shown technically in many ways that this is probably true. So okay, so that's the end of this lecture. The Friedman-Navidi case is a difficult case which we might cover. On the other hand, there's the next chapter, which is hierarchical Bayes. So I'll have to think about what to cover for next time. But anyway, okay, so that's the end of this lecture.